Okay, other uses for ultrasound. So, ultrasound is also used for medical imaging. We talked about that a little bit yesterday. Somebody said they were having one done of their kidneys. You can have them done of your thyroid or other abdominal organisms. And we talked a little bit about how they worked yesterday. The reflected pulses form a picture in terms of how distant from the source of sound the object is, and they bounce back and you actually get a three-dimensional image. And this is exactly the way that dolphins and bats locate stuff. Okay, so you know that the speed of a wave depends on what? Well, frequency and wavelength are related to the speed. The speed of the wave really depends on the medium in which it's traveling. That's what controls the speed of a wave. And that's true for any wave, for any kind of physical wave, whether you shake a pan of Jell-O or, start splashing in water, or you yell or you play a trumpet, whatever. The speed of the waves is dependent on the medium in which they're traveling. Now, when you have a wave traveling through a medium, and we're going to, again, generalize this as a transverse wave, even though, remember, sound waves are what? Longitudinal waves. They're not transverse waves, but to get our puny little brains around them, we very often picture them as transverse waves. They are not transverse waves. I'm going to say that every time I draw a transverse wave. Okay, when we have a wave traveling through a medium, what's really happening, if we think about all the particles in the medium, what's happening if we think back to our little dowel rod wave machine with the yellow tips? Particles are just going up and down, right? Up and down in place. The particles are not moving like this. They're just traveling up and down in place, and they transfer their energy to the next particle, and it moves up and down, and the next particle moves up and down, and the next particle. You get the picture. It's not all that exciting. So, what would cause a wave to travel faster? Based on thinking about it in terms of kinetic molecular theory, which harkens back to chemistry. If the atoms were closer together, then the wave would travel much more rapidly, because those atoms are close enough to exert a very strong pull on one another. So, from gases to liquids to solids, in which medium do you think waves travel most quickly? Solids. Waves travel very rapidly in a liquid. Have you ever watched, I don't even know if they show these anywhere. Did I say, yeah, solids, sorry. I went down the wrong track there. Because I was thinking of tracks. I don't know if they even show the kind of old westerns somewhere in the backwaters of the television universe that were a feature of my childhood. Okay. Have you ever seen in one of the old westerns the following scenario? Okay, so our hero in our old spaghetti western comes up to the railroad tracks out in the middle of nowhere and very wisely says, wait a second. Bends down, puts it's always a his, ear to the railroad track and says, there's a train coming. Yeah, they're listening for vibration in that steel rail. Because that steel rail is you're going to get the sound wave, the vibration, long before you hear it in the air. Okay? So now that makes perfect sense, right? That waves would travel more rapidly through a solid than a liquid or a gas because the particles are more closely packed. They're close enough to exert very strong pull on one another. Fast travel, right? Makes perfect sense. Good. So after solids, which one do you think would be the next speediest medium for wave travel? Liquids. And we have lots of swimmers in here. If I drop a beeping something into the pool, you're going to hear it underwater much more rapidly than if I put it the same distance away from you in the air. That sound is going to travel faster. Okay? So that makes perfect sense, right? Fantastic. Now let's get to the weird part.
Hold on. Because when you're underwater and you try to yell, no one can hear you.
Well, the sound is muffled, and I believe the amplitude of the waves is smaller, but the speed of the waves is greater. So amplitude is most directly correlated to volume. And if we draw that, terribly drawn, but this is an attempt at drawing two waves that have the same wavelength but different amplitudes. So the wavelength and the frequency would be the same for these. The amplitude would be different, the distance from, you know, top of crest to bottom of trough. And the amplitude is most closely related to volume. So I believe that's the case. But we should definitely look that up later. Temperature. Of those three phases of matter, and it feels like we're in chemistry as we talk about this, of those three phases of matter, which is most affected by temperature? Gases. The temperature dramatically affects the density of a gas and the volume of a gas to the point where we have things like the ideal gas law to compute new volumes at varying temperatures and pressures. So if we're talking about a sound wave traveling through a gas, and we're saying that how close together the particles are affect the speed of the sound wave, temperature is going to play a role. So there's what you would intuitively think, and then there's what actually happens. I hate it when science works like that. So the way that I always remember this is, it's exactly the opposite of what you would expect. As you heat up a gaseous mixture, sound travels faster through it. Despite the fact that the molecules move farther apart. I know, I hate it too. When you heat up a gaseous mixture, there are more collisions between the particles. And those increased collisions increase the rate at which the energy is transferred. So sound will travel more slowly in 0 degree air than it will in 30 degree air. For all gases, we're talking right just about gases right now. We're going to talk about the liquids and the solids in a little bit. We're keeping it weird with gases right now. So exactly counter to what you would expect, because as those particles have increased opportunities to collide. Here, I'll draw my gas particles. Even as they move further apart, they're vibrating faster, which means more chances to collide. Fa-chung, fa-chung, wham, bam, slam, zoom, zoom. They're moving around really, really fast. That's the whole idea. The faster those particles are moving in a gas, the faster the energy is transferred. So, higher temp in a gas means increased wave speed. It does not fit with the whole, the closer the particles are together, the faster the waves travel. It is the exception to that. Now, with liquids and solids, because do liquids and solids expand a lot based on temperature? They expand some. They do. But they don't expand in any way like a gas does. You know, where a gas will triple its volume if you triple its temperature. You can triple the temperature of a liquid or a solid and you're going to get a minuscule little budge in volume. You're not going to get much because they're much more closely bound. They've got powerful attractive forces. Their kinetic energy is not enough to overcome those. They are not flowing freely. So in liquids and solids, temperature doesn't really make much of a difference. And that answers your question. You know, 1 degree water, 99 degree water. Not much of a difference in terms of how fast sound will travel in it. Not that you're swimming in 99 degree water, or you shouldn't be. But the temperature and wave speed relationship only holds for gases. And we hit on this a little bit yesterday, that sound waves are three-dimensional, so what you're really seeing are spheres. Those circles that we represent them with are actually spherical objects, and you can walk down the hall envisioning little chatty freshmen as giant bubbles with membranes of sound coming off from their heads in waves. You can also do this with little yappy dogs, and that's kind of fun. We represent them as concentric circles, which is just a cross-section of that spherical wave pattern coming out from the object. So we call the compressions that are moving out from a vibrating object wave fronts. And if you have ever been close enough to something that you could actually feel the sound coming off of it, how many of you have been close enough to something you could feel the sound coming off of it? Okay, yeah, and cars with really ridiculous stereo systems are a good example where the windows are shaking. Those are wave fronts hitting the window. And those are actually compressed air particles coming up in waves and smacking against the glass until the glass begins to vibrate. Each one of those circles is just a cross-section of a sphere, and the distance from here to here is a wavelength. Badly drawn, but that's a wavelength. Let's try that again. There. Huh? Yeah, that's still pretty bad. Well, you know what? Lambda. There we go. That distance. That distance. How's that? That's lambda. Because the compressions, remember, correspond to either crests or troughs, and the rarefactions correspond to the inverse. So, what would this big empty space in here be if each of those circles is a compression? Rarefaction. Yes. Right. It's the extended area in between the zones of compression and a transverse wave. So, if we look at all of these concentric circles, all of these sound waves coming off of our little vibrating object, we can draw a line through all of them that cuts across them perpendicular to the wave fronts. We call this a ray. It's not that important in sound waves, but it's hugely important when we get to light in the next chapter. So just remember that term. Again, this is a concept that is going to come into more play in light when we're talking about solar death rays and the like. If we go way far out from our object and we get far enough out, these circles get pretty big, and a section of those wave fronts really start to look almost like parallel lines. And we call those plane waves, and we act as though they are one-dimensional waves that are just traveling. So imagine waves on a beach just rolling in straight lines, even though these are obviously actually chunks of a concentric circle, but we treat them differently, and that's much more important when we get to light, but it's in this chapter. As our little car is moving in this direction, the sound waves ahead of it are compressed, and the sound waves behind it are actually extended outward. Light, but we have compression of the waves, and if you imagine, have any of you ever thrown a stick into a pond for a dog?
I threw a stick somewhere.
Okay, you should go home and find a dog in a pond, or make friends with somebody who has a dog and access to a pond, and I want you to go out and I want you to throw the stick for the dog, and it has to be a water-loving dog.
That's my dog all the way.
Okay, little lab or something, throw sticks out into a pond all day, dog will be happy. As the dog is swimming out, okay, so as we're looking down on the dog from our little hover position above the pond, this is what the waves look like. It's essentially the Doppler effect visualized, because the dog is compressing the water ahead of them, and the ripples out behind them are extended, so you get these big, long teardrop sort of shapes. It looks like a V coming off of the dog. When the dog gets the stick and heads back towards you, that whole thing, when the dog turns around, the whole thing's reversed, and the V is coming at you. Okay, if we look at, this is a pretty good image for this. If we imagine the police car and the siren noise, and we can see how these waves are compressed. Well, if the waves are compressed, they hit you more frequently, which means they have an increased frequency. They hit you more frequently, they have a higher frequency of hitting you. If you're out behind, those waves are hitting you less frequently, they have a lower frequency. Remember, pitch and frequency are not the same. But we perceive higher frequency sounds as being higher pitched. We perceive lower frequency sounds as being lower pitched. So the pitch of the siren changes as the object goes past you. Okay, so this is exactly what we just said. Because frequency controls our perception of pitch, the siren, the train, the person yelling, whatever it is that's coming at us, sounds like it's higher pitched than it does once they pass us. We hear that drop in pitch as the object goes past us. So, you are all familiar with Doppler radar because every single radio station, TV station, National Weather Service, every weather forecast you've ever heard uses Doppler radar these days. That wasn't always the case. 30 years ago, Doppler radar was the big thing. It was new. They weren't using it yet. So, we use Doppler for weather radar. More importantly, the Doppler effect was first noticed with space. So when we're observing objects in space, because the same exact phenomenon occurs with light waves that does with sound waves or any kind of waves, when we were observing objects in space, we're gathering light into telescopes about them from a long way away. If the object is coming towards us, the light waves are compressed, and the light waves shift towards the shorter end of the light spectrum. The shortest of the visible light waves are what color, do you know? The 400-450 nanometer range is blue. It's blue. So if objects are coming towards us, like stars and stuff, their light is shifted towards the blue spectrum. If objects are receding away from us, then the frequency of their waves is extended. They are perceived as lower frequency, and they are towards the red end. So lower frequency, longer wavelength, those are the red waves. And so we talk about red shift, blue shift. So the joke is, in physics circles among physics geeks, you can tell this to your physics profs next year if you're taking physics next year. Yeah, there was this police car chasing me, but I was going so fast, all I saw was the red lights. Ah! Never mind. Tell it to your physics prof. They'll think it's funny. You are all familiar with this phenomena. This is decibel level stuff. So, when we have a vibrating object creating noise, it's creating vibrations. Those vibrations hit you. We said that if you're standing close to Hayden's car, when his volume's turned way up, your entire body is going to vibrate in response to probably mostly the bass, I'm guessing, as the windows rattle and shake. We can measure the intensity of that sound. We can measure the intensity of that sound. It's actually, intensity of sound is the rate at which the energy is moving. So remember that waves are a disturbance in a medium that transfers energy. The rate at which energy is transferred is power, if you think back to Chapter 5. So really we're looking at power, and it's power per unit area is the equation for intensity. And intensity is watts per meter squared. Now you may be asking yourself, where are the decibels? So we said that the intensity of the sound was the power divided by the unit area. Well, remember that even though we represent these sound waves as circles, they are really what? Spheres. So we're talking about the surface area of a sphere. So we have 4 pi r squared. So intensity is equal to 4 pi r squared, and the radius is just how far you are from the sound source. So that's pretty easy. The further you get out from the source, the less intense the waves are. But because of this exponent here, is it a linear reduction? Is it a linear reduction in intensity? No. It's what? It's exponential. It's an exponential reduction in intensity with the amount of space that you put between yourself and the sound. Factor of 4.
So if you triple it, it would be...
Factor of 9. Yes.
So you basically square within the number.
Yes. A?
No, he's...
Are you picking on Stephen? If I have to stop this car. Whoops. Okay. It's going to vary slightly from individual to individual,
I'm sure you've
based
explained
on
stuff
based
to me.
on shape of your ear canal, sensitivity of your ears,
that's
all that stuff.
I could, but they're
What
fraternal
about even
twins.
twins? It's completely different.
Well, it would depend on environmental factors.
Huh?
If you have one twin,
Just take a
so
picture.
my grandma was a school cook, and she was a school cook at Crestview, in the old building that they just tore down a few years ago, and the cafeteria in that building was in the basement.
Really?
It was a 1918, 1913 construction, you know.
Wait,
The cafeteria was, yeah, yeah, and it was a low ceilinged room. You know, I mean, ceiling's probably a little bit shorter than this. Wooden floors, clear plain walls, and you pack 200 kids into it at a time. And it was an absolute, and stainless steel everything,
Oh,
all
bounce
open.
off everything.
And it was an echo chamber.
Yeah.
My grandma had significant hearing damage by the time she retired due to, I mean, it was an environmental, it was work environment. It was, you know, she wasn't running loud construction equipment. She was listening to 5th through 8th graders every day in an echo chamber. And, you know, Grandma kept the TV up really loud because she had had hearing damage. So, yeah, that, you know, that kind of hearing damage really changes your perception of loudness. Okay, we're going to look at audibility. So, audibility is how well you can hear a sound. And there's a chart on page 49 in your book. It's this weird curvy structure. So there's also what we call the threshold of pain up here. So the threshold of pain is the point at which a sound actually becomes painful to your ears. And for some of you, that happened when we did the hearing test up near 20,000 hertz, where it actually starts that you want to cover your ears. And there have been military experiments with sound weapons where you can generate a tone that's painful to people, that makes them want to cover their ears and drop. There is another threshold here where you can sense, you feel the tone. Human speech, it will not surprise any of you, comes right smack in the middle of the human hearing range. And again, this is an evolutionary feature. Humans who could hear other humans well to cooperate and take care of other humans' needs survived and reproduced. There are a couple thresholds in this chart, and this chart is reproduced in your book. Thresholds of hearing. So the volume or the intensity of sound that you can hear depends on frequency. And there are some things that we can hear at very, very low intensity, so very quiet. That would be where human speech exists. We can hear other humans whispering. There are, you know, that 20 hertz tone we don't hear when we did the sound test. You all heard the 60 hertz tone. At a low volume, you would be less likely to hear the 60 hertz tone. And if you noticed, even though the volume did not change on that recording, it seemed to get louder in the range of human speech, because that's what we hear best. The loudest sounds the human ear can tolerate also varies by frequency. And again, in the range of human speech, that's where you can start to get pain at lower intensities, because that's the range that our ears are most sensitive to. Oh, relative intensity. The decibel scale is not it's not as scientific as you might think. So the actual base unit for relative intensity is the what? Looking at that name, what is it? It's a metric prefix. It's the bell. A decibel is what we actually talk about. So the decibel scale is dimensionless because it's just a comparison. It's a ratio of the threshold of human hearing compared to the sound, so how close it is. and it is a logarithmic scale, which means if you multiply by 10, you add 10 decibels. So if you add 100 decibels, how much more intense is that sound? 100 times more intense. Okay? Every time you go up a decibel, you multiply. Okay? There's a chart on 490 in your book that's useful. We're going to talk briefly about forced vibrations in resonance. You experienced this phenomena when you played around with the resonator boxes, the big wooden boxes with the tuning fork sticking out of them. The tuning fork was louder when it was screwed into the resonator box. Why?
For me.
Well, not quite.
So it was vibrating more than before.
You had a larger surface area to vibrate, so that vibration was transferred into the wooden box, and then the wooden box vibrates. And so that generates a much bigger disturbance. A guitar is just a big resonator box. So the strings on the guitar vibrate, and they transfer that vibration via the hole in the box into the box, and then that whole box vibrates. And if you ever heard somebody play slap guitar, where they slap their hand down on the box, that deadens the vibration, and it'll stop the tone. And then, yeah, it is.
Yeah, I really
and that's just a resonator box. That's all that is. Your multi-pendulum system in the lab should have developed resonance. I think we had some issues with that.
The lab was a little messed up.
But we'll try that again. So when we get a vibration in one object that's transferred from another, we call it sympathetic vibration, and you can it's forced vibration or sympathetic vibration. And like I said, the guitar resonates because you get forced vibration from the strings into the body of the guitar. The energy transfer is facilitated. You can transfer energy over a larger surface area and more efficiently out of the room, so it amplifies the sound. And that's where we're going to stop today.